A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. In today's lecture we will discuss the magnetic properties that are present in fluid and how we can utilize this in different type of applications. So this lecture is a part of nanophysics and technology course having the course code of PHY445. Basically we need to know magnetic particles in fluid. So most clinical and biotechnological applications of magnetic carriers involves suspension of particles in fluids. So what happens when we review some of the basic principles governing the behavior of magnetic particles in fluid? So there are several factors involved to study this. Some of the forces involved in this phenomena is the force of applied magnetic field on the particles. That is actually the external force or external magnetic field force. The other is the viscous drag force. If we compare the same thing with the magnetic particles in bulk material and in solid material, so this is a bit different because some other forces also arises, and that just like we can consider the viscous drag force that was actually absent in the case of solid materials. So the viscous drag forces are present in this case. We have interparticle magnetic forces as well. There is interparticle electrostatic forces as well that are present, and finally there are interparticle entropic forces that are also present and play a vital role. So how we can discuss the single magnetic particle in fluid? This is a single magnetic moment, that is a uniform magnetic field tends to orient that magnetic dipoles. So what happen? This is just like an electric dipole inside an electric field. So a uniform force is applied, and the tendency or the force try to align this magnetic moment in the direction of field. Here in this case, this external magnetic field will try to align this magnetic moment in the direction of field. So uniform field does not exert translation force on the dipole. So forces are now north and south poles are balance each other, and it is not a translatory motion, but it is actually the alignment of the moment in a particular direction. Just like this is the magnetic moment, it is present in different directions. So simultaneously, at the same time, two forces are acting on the one at north and other is at south pole, and the resulting effect of both the forces is to align the magnetic moment along the direction of field. So that will align the magnetic moment in the direction of field. So this is the single magnetic particle in fluids. So and this is alignment in a particular direction. When it is aligned, when the magnetic moment is aligned, so there is no further force acting on it. Of course it is force, but it is already aligned, so it is no further movement of this magnetic atomic moment. If we have single magnetic particle in fluid, so what will be the case? So a field gradient is required to exert a translation force on the dipole, and just like in figure it is clarified that the stronger force on north pole and a weaker force at south pole. This is just like a non-uniform magnetic field. In previous cases what we had discussed, that was a uniform magnetic field, but in this particular case we are considering non-uniform magnetic field. So this net force causes translation as well. Just like magnetic field gradient, here we can see the magnetic field gradient that is present in a disc shaped magnet. So we have a simple bar magnet generating magnetic field gradients. So the gradient tend to be larger at sharp corners of magnet. So what happen? Fine or sharply pointed magnetized objects generate high field gradient, and this high field gradient is used in magnetic separators. Just like in this particular case, we want to separate something, that is actually magnetic separators. So fine wires with high accessibility and low remanence used in a column. So magnetic particle bearing fluids pass through columns with applied field. So what happens, particles are attracted toward the wire. So particle can be released by removing applied field to demagnetize the wire. We have a particular number for that, that is actually called as Reynolds numbers. So Reynolds numbers of an object in a fluid is the ratio of inertial to viscous forces experienced by the object. So that is actually this micron to submicron particle in water having very low Reynolds numbers, just like its velocity is proportional to external applied force, and just like object reach their terminal speed almost instantaneously. So we have free field gradient for it, that is applied to small magnetic particle in fluid, just like speed of the particle is proportional to the field gradient force. Field gradient force is proportional to the moment on the particle, that is actually the magnetic moments or the atomic magnetic, the atomic origin. We already discussed this from the atomic origin of magnetism. And indirectly, if we see the magnetic moments in the particle is proportional to the volume of the particle, and what happen, the speed is proportional to the volume of the particle. So what we summarize from all this discussion, the proportionality between different factors, that larger particles moves faster in field gradients. So field gradient applied to small magnetic particles in fluid would happen, and how we can discuss it. So magnetic separation techniques proficiently removes aggregates of particles. So magnetic microspheres will move faster than nanosphere. And what happens, the more likely there might be interparticle interaction, that is actually called as aggregation. So more likely to occur as a magnetic moments on particle increases due to interparticle magnetic dipole interaction. So there is if there is very large aggregates leading to the precipitates, there will be gravitational forces significantly present there. So the aggregation may be of two types, whether it is reversible aggregation or it might be irreversible aggregation, depending on the nature. In the case of reversible aggregation, what happens, the particle aggregate under the applied field. All the particle aggregate under the applied field, and removing field lowers moments on particles sufficiently that repulsive forces dominate, and that is the effect of that. So if we consider irreversible aggregation process, so what is the effect of irreversible aggregation process? In that case, if we apply the field causes aggregation, so the proximity of the particle to each other results in mutual induction of dipole moment even in zero applied field. So the effect is that there is attractive magnetic interaction within aggregate domain. So this process is actually called as a irreversible aggregation. So just like we have demagnetizing interaction in clusters, it's also possible. Normally the temperature do the demagnetization, but in some cases we have some demagnetizing interaction also possible in cluster. Here we can see the magnetic moments are oriented in different directions. If it is oriented in the same direction, we can say this is a line and it have magnetization, particular magnetization, leading to the total magnetization of the systems. If the magnetic moments are aligned in different directions, so they will cancel the effect of each other. So the particle in close proximity will affect each other. So the moments tends to arrange themselves such as to minimize magnetization of aggregate. So this is actually the demagnetization process, and cluster of particles may show reduced susceptibility in low fields because they cancel the effect of each other. So we have magnetic carriers, and we can design of magnetic cages is also possible. Just like if we have high susceptibility general desire require high susceptibility general desire is desirable, and we know low magnetization, then the magnetic moment can be switched off. How is possible? High interparticle repulsion to reduce it can be done with high interparticle repulsion to reduce aggregation, and the aggregation is possible with the help of this the interparticle repulsion leads to the reduction in aggregation, and that could be possible with the help of electrostatic repulsive forces and entropic repulsive forces, and this just like these factors are needed to overcome the interparticle attractive magnetic forces that are determined by the chemical understanding of the particle coatings. Here we are going to understand the design of magnetic microspheres. I mean, magnetic moments are present and that are magnetic nanoparticle arranged in different directions, and we need to calculate, we need to design the magnetic microsphere. So this microsphere could be designed by making microsphere from the aggregate of super paramagnetic nanoparticles, and in this super paramagnetic nanoparticles give high susceptibility and zero magnetization, and that is only possible when the aggregate micron size yield faster movement in fluids. This is the hysteresis loop, and we can use the same material for various sort of application, especially for the treatment of cancer and for more application as well. So particle for special application are used, just like particle for hypothermia therapy, that is used. Magnetic hypothermia therapy involves the application of AC field to heat the particle, and heat generated per field cycle is proportional to the area within the hysteresis loop. Here we can see the area within hysteresis loop, and we can change the area of the hysteresis loop by changing the nature of the material, so that can change the property of the material, leading toward change or increase in the performance of the material. Here we can see that the curve is very different from the earlier curve, the hysteresis curve. You see the hysteresis curve for hypothermia therapy that has been changed here. You can see there is quite difference between the two, and even the third one as well. So there is therapeutic AC field amplitudes are limited to avoid nerve stimulation, because it can damage maybe some other nerves. So that is why we want to only affect those cells which only damage those cells which are affected. So therefore we need to narrow the hysteresis. So particle with low caricitude but high MS are preferred in this particular case. So we have particle for Brownian rotation studies, just like we have the gas molecule, or even in water molecule there is a Brownian motion, or moving in it, particles are moving in different direction with having no net directional motion, that is actually the Brownian motion. So here we can consider the same phenomena over here, the particle for Brownian rotation studies. So we have magnetically blocked particles required for this particular case. External fields applied, so must stay in suspension. So what happened? We need to observe time dependent magnetic behavior of fluids due to physical Brownian rotation of the blocked dipoles. So that could be a line. If there is no extra here the external field is applied, and the effect of this external field is to align all the dipole in the field directions. The force is applied, and the effect of this force is to align the dipole in the direction of field. If you look towards each of the magnetic moment present here in this figure, all are tried to align, or some are perfectly aligned in the field direction, and that is giving net magnetization. But in this case, when there is no value of H, the external field is equal to 0, so what happened? The magnetic moment are randomly oriented, just like if we consider in case of conductor, the free electron are randomly moving, that is actually with the thermal velocity, that is called as VT, that is thermal motion of the electron inside the conductor. but keep in mind the thermal motion is not the directional motion, it's randomly moving without no external specific direction. But when an external electric field is applied or a potential difference is applied, so what happened, the electron are drifted in a particular direction, so that is called as the drifted motion of electron, and the velocity in this case is called as a drift velocity, that is called as Vd. In the same case, when there is no field applied in this magnetic moments, it is randomly oriented in different direction. Here looking toward this figure, none of the two are in the same direction, so this is because external h is equal to 0. But if we apply some h, you see some of them are perfectly aligned, but some of them are trying to align the direction of field depending on the strength of external magnetic field. So this is the magnetic block particles required for this, and we need to observe the time dependent magnetic behavior of fluids due to physical Brownian rotation of block dipoles. So this is something we had discussed about this is the basic phenomena, very interesting phenomena describing the motion of this part and describing the motion of this magnetic moments, and that elaborate how the magnetic moments are aligned due to the external field. If you remember this, we have also studied in electric in the case of in electrostatics as well, where we consider a magnetic dipole, an electric dipole. An electric dipole was nothing but that was actually two charges of opposite nature was separated, two charges of the same magnitude was separated by a distance t, and its dipole moment was called as P is equal to QD. So what was the effect of this? This dipole was randomly present there when some external field was applied on it. So this dipole, a force was applied on this, and the effect of this force was to align the dipole, the electric dipole, in the direction of external electric field. The same thing we have studied in magnetostatic, where we have a magnetic dipoles, and the magnetic dipole is present. Magnetic dipoles is just like north and south pole, a magnet, because we cannot have magnetic unipoles. So we have a magnet having north and south pole. So when an external field is applied on it, so what happens, initially it is randomly present. So when an external field is applied, what happen, it tried to align in the direction of field because a force is applied, and the effect of this force is to align this dipole in the direction of field. I mean to align this magnetic moment in the direction of field. So in some cases here, just like in this case, we have it is not even, it's some most of the magnetic moment like this one, this one, this one, this one, this one, these are actually aligned, but these are perfectly aligned, just like 1, 2, 3, 4, 5 and 6. These fixed magnetic dipoles are perfectly aligned, but the other, just like this one, and this one, and this one, this is 1, 2, 3, 4, 5, 6, 7. These 7s are not perfectly aligned, though it is aligned much more due to the external magnetic field. It depends upon the strength of magnetic field initially when the field is applied, and that is why we have hysteresis loop, because when all magnetic moments perfectly align in the direction of field, we have saturation magnetization. So if here we increase the strength of magnetic field, the force acting on this magnetic dipole to align this dipole in the direction of field will increase it, and definitely, because more energy is required to align this magnetic dipole in the field directions, so it will try to align, and that is why its magnetization will increased, and further increase in the magnetization, further increase in the strength of external field H, it will further align the more dipoles in the direction of field. So a moment will rise when all the magnetic domains will perfectly align in the direction of field. So this particular case is called as the magnetization at this particular stage is called as saturation magnetization. If you further increase the value of H, there will be no increase in magnetization. Because why there is no increase in the value of M? Because there are no more magnetic moment to align. There are no more magnetic moment to align. So that is why we have saturation magnetization. And the same concept is already clear in the case of hysteresis loop, because when we remove or we change the direction of H, so they will try to disalign at time reached when there is zero magnetization, and then it will try to align in the other direction. So this is something about the magnetic nanoparticles in fluids, and some introduction about the magnetic nanoparticles in fluid and their discussion. So this is something for today lecture. Thank you very much.